All right, kia ora. So here is our first task for this remote learning. This is for week 5 of term 1. There's going to be basically just 2 tasks for you guys to do this week. The first being this lesson, and then the second being a CPR quiz, and I'll explain what that is in a moment. But really what I want us to do for today is describe and explore physical properties of ionic solids. This is the last type of solid that we have to worry about. So with today's success criteria, you should be able to define and explain an ionic bond and also the properties of that ionic solid. And remember, you should be able to then link it back to the particles and to the forces that are present. So let's first talk about the structure of ionic compounds, and this hopefully should be something that's familiar to you guys because you did ionic compounds last year with acids and bases. Basically, in this case, we are dealing with ions that are charged particles, and they are set in a 3D lattice, and that 3D lattice is very specific in the structure, and that's because you have a cation that's surrounded by anions and vice versa, so you need that positive and negative charge alternating. And just a reminder what ionic bonds are. In this case, it is that force of attraction between a positive cation and a negative anion. Basically, an ionic bond is formed because the electrons from one atom gets transferred to another, and that's going to result in one being positive and one being negative, and though that positive and negative attracts together, forming that ionic bond. This is an example of an intramolecular force. Remember, those ones are traumatic to break, require a lot of energy, so ionic bonds are relatively strong. And here's my little joke. My name is Bond, ionic bond, taken, not shared. And that is the key difference between ionic bonds and covalent bonds. So we've been talking a lot about covalent bonds, which is the sharing of electrons. In this case, there is no sharing. It just gets transferred. So here's some examples of ionic bonds. So we have sodium that has one valence electron. Now, in order for it to gain more stability, it wants to drop and get rid of that electron. And chlorine, luckily, only needs one to complete its shell. So that's where that electron's getting transferred to, and that's what you commonly known as table salt, sodium chloride. This results in a positive cation and a negative anion, and so these two will attract, forming that ionic compound. And if we look at their electron arrangements, both of them are now stable. There we go. Strong electrostatic attractions. Also be mindful that some atoms will have multiple electrons they want to get rid of or multiple electrons that they want to gain. So calcium is a good example of that. It has 2 valence electrons, and so one is going to go to each of the chlorine atoms to form chloride because they each only need one to fill their shell. And so in this case, when it comes to electrostatic attraction, you're going to have 2 chloride ions for every 1 calcium ion to make it that neutral ionic compound. So let's look at some of these properties. So first off, as I said, they have ionic bonds, and those ionic bonds are an electrostatic force, and those are very, very strong. So they're not easily overcome. And because they're not easy to overcome, that then ties into the fact that it's going to need a lot of heat energy to sufficiently have enough energy to break those ionic bonds. Thus, a state change, and thus the high melting and boiling point. So it's really hard to actually get molten salt. You have to really, really heat it up. These guys are also very hard, and that's because, again, they're being held together by those strong ionic bonds. On top of that, the ions are very closely packed together, and so they have a strong bond that's being very close. These guys, however, are brittle. It's very easy to crack ionic solids. They do not handle stress or pressure well. And you then have to think about, why is that the case? We know ionic forces are strong. What is then the issue? Well, the problem is when you apply stress, you're then moving the ions slightly, and when you move those ions, you're now going to align the like charges together, and we know like charges repel. So the next image is a good one to see it, but basically they repel, and that causes the crystal to split, thus the brittle component. So here's a nice image that I find really helpful. Oh, let me just get those out. Basically what you see is an external force that's being applied, and with that external force being applied, you then temporarily get that arrangement of like charges, so positive and positive, negative and negative, positive and positive, and that's going to cause the repelling and the cracking. Cool. Next thing to talk about then is solubility. Be mindful, I will do a whole separate lesson on solubility, so if you don't quite get it yet, that's okay. There is other bits of the story I haven't quite told you yet, but I'll try my best to kind of explain it. So when we talk about solubility, we're just saying, is it able to dissolve in water? Or sorry, I should say, is the substance able to dissolve in the solvent? Most commonly, that solvent is water. When it comes to ionic solids, that would really depend on the force of attraction to itself, so the ions to the ions, versus the force of attraction to water. And the reason why these ions are attracted to water is because water is a polar molecule. Now, we haven't had a chance to cover polar molecules. I will do that later because I do want to do Lewis structures first before I talk about polarity. The main thing that we have to remember with polar molecules is that that molecule, like the covalent molecular solids we've been talking about, some of them have a slight positive and a slight negative end. And this is the result of the unequal sharing of electrons. So if one atom is very electron negative, it will pull the electrons closer to it, making it slightly negative because electrons are negative. The absence then of those electrons that are getting pulled away results in a slight positive. So they're not a charged particle, these molecules. They just have a slight positive and a slight negative. But that slight positive and slight negative is enough to attract the charged ions, such as the cations and the anions. And what you'll see here is that chloride is a negative ion, and it's attracted to the slight positive end of the water molecule. Sodium is a positive cation, and it's going to be attracted to the slight negative end of the water molecule. And you see that little, I think that's a delta symbol. It just refers to how we annotate slightly. Cool, so here's a little video for us to kind of see it in animation because I think it helps to see it. So this is how water can dissolve a salt. So that's just a water molecule. And you can see the salt crystal, which is just sodium chloride, your normal table salt. Now, what I was just mentioning in the previous slide, water is a polar molecule. We know that there's a covalent bond here between the hydrogen atom and the oxygen atom. However, the oxygen atom is more electronegative than the hydrogen atom. So these shared electrons are actually getting pulled closer to the oxygen atom, and that's happening in both cases. And because electrons are negative, it's going to cause the oxygen end of the water molecule to be slightly negative. These hydrogens, with the lack of the shared electron being nearby, and the fact that it only has that one proton in its nucleus, makes it slightly positive. And again, we can see with sodium chloride, the sodium ion is positive because it's lost that electron, given it to chloride. Chloride has gained that electron, so it's negative. Remember, it has one more electron than proton. In this case, one less electron than proton, thus the charge. Cool, and then you can hopefully see that the opposite colors, and that goes to show how the positive end of the water molecule is attracted to the chloride and the negative end of the water, whereas the oxygen is attracted to the sodium ion. And so basically it'll keep doing this until it's pulled apart the whole chloride or sodium chloride ionic solid and thus dissolving. Now, not all ionic solids will dissolve. Like I said earlier, it depends on the attraction to the water molecule versus the attraction to itself. And you would have done that last year, hopefully, with the types of reactions internal, where you're doing precipitation reactions. And we'll do that again with the ion identification internal. So you'll get to see, ions that are ionic solids that do dissolve and ionic solids that do not dissolve. Cool. So electrical conductivity is the next thing here. Remember, as a big picture thing, you should always be referring to its ability to conduct an electrical current. And for that to happen, it just needs some sort of charged particle to do that. We learned in graphite and in metals that's going to be your electron. In this case, with ions, it's going to be, or ionic solids, it's going to be ions. Cool. Now, the thing to remember about ionic solids is that they can only conduct electricity if the ions are free to move. Remember how I said earlier there's that set 3D lattice, and that set 3D lattice prevents them from moving. So we need to figure out a way to make them mobile. The whole key of it is that it needs to be mobile. So when it's in the solid state, it cannot conduct. They can conduct electricity when they are dissolved into water, or if they're molten, aka they're in the liquid state. In those two instances, those ions are now free to move. This is a really common question they love to ask about ionic solids electrical conductivity, because there's this if this then that capability to that answer. So it's conductive in this situation, it's not conductive in that situation. So in this example here, we have the ionic solids, and then in this picture next to it, you have it dissolved in water, and you can actually see that it's conducting electricity. Hopefully when we're back, we can actually do this experiment and we can test out plain water, salt on its own, and graphite, so you can see all the different kind of conductivities. And like I said, the whole purpose of this is that we get them to be mobile. So if they're in the solid state, they're stuck in that 3D lattice and those ions aren't going anywhere, but the moment I melt it or I dissolve it into water, the ions can now move. Here's another cool video, and this one shows molten salt. So here's my circuit, and we can see that the circuit works because I can touch those two electric wires together. So we know metals are conductive. And this is just your normal sodium chloride table salt. So when you pour it in, nothing's going to happen with that circuit. It's not a full circuit because those ions are locked. But when we start heating it, we can get the ions, or the ionic solid, to melt, and you'll be able to see the light turn on. Isn't that cool? It's also just cool to see like the liquid form of salt. And then once it cools down again, the ions get stuck in their set lattice and the conductivity is no longer there. Cool. All right, so just some reminders of important terminology, because it's really important that you're careful with how you're writing it. There are times when you want to be general, and there's times when you want to be more specific. So when you're just talking about electrical conductivity, you want to be general and just say a mobile charge particle, because that covers all your bases of electron and ion. However, once you start talking about specifics, so like a specific type of solid, then you should be talking about the particular charge particle that's allowing for that conductivity. So with metals, you should be saying electron. I should also say with graphite, you should be saying electron. With ionic solids, you should be using the term ion. If you switch around these terms and you use them interchangeably, or if you are general with your statement and just say mobile charge particle, you won't be able to get an excellence for that, because they are going to look at that vocabulary. And then here's a summary of the identification key. Remember how I said that identification is the most important part for this type of solid question, because it sets you up to do the long answer, because you have to tie back to attractive forces and particles. If you misclassify, then your justification is going to be off. So do kind of keep that in mind. It's relatively straightforward. And in most cases, they will only give you one of each type of solid. Cool. Kapai, really good work today. So we worked on describing and exploring the physical properties of ionic solids. By the end of this lesson, you should be able to define and explain an ionic bond and also talk about their properties and link it back to the atomic structure to Y. So now it's up to you to move on to your Mahi choice. Remember, all those follow-up activities are listed on my Google site, and all the resources are on Google Classroom. You aren't expected to do all of it. It's just to give you some options that are differentiated.